Hello, welcome to the second ODS Paris Meetup. I will talk at the beginning about a bit ODS community, so you will have a notion what is it. It's a Slack community, mostly Russian speaking, but also there are a lot of English speaking users. And also ODS community have a Telegram chat where you can see every news or something that happened in data science and machine learning field. So after there are in the Slack channels, there are some channels related to frameworks where you can ask directly creators of these frameworks and ask them questions. If you have any bugs, you can report it, or you can even open source contribute to open source. So you have several frameworks that you can find channels in the Slack community. So it's GPT, Catalyst, or image augmentation library, augmentation, and Ebonite. It's for reproducible ML. It's like a kind of framework to be able to load your model in the Docker or something like that and reproduce it after that. So there are also channels competitions related to Kaggle, and if you want to join, you can fill the form, but it could take 2 to 3 weeks to approve because it's all approved by hand. Yeah, I would like also to thank Anton and Evgeny, who are also participated a lot to this meetup. And you will also see them in the networking part. So let's stay tuned, and thank you, Anton and Evgeny, a lot for a lot of participation to this happening. So, and don't miss our next event. It will be in 1 week. Recently, there were a Kaggle competition that ended 2 weeks ago, and Artem Zhvalkovsky, he won the first place and with his team. So he will talk about his solution, about this tweet sentiment extraction competition. Also, we'll have a small talk from Philip Singer, who is a double grandmaster now and top 4 in all Kaggle. And also he will talk about his 11th place solution and solo gold medal and the way how he received it. So Artyom told me that solutions were quite different, so it should be interesting. Don't miss it. It's in 1 week, 7/7 at 7 July at 7 o'clock. So today I will tell you a little bit about what to expect. Maggie from Renault Digital, she will talk about how to put ML models in Tensorflow into production. So then we will have some questions and video networking. Don't miss it. So Maggie, she now works at Renault Digital, and also she has a PhD in signal processing and information theory, and she is a part-time professor in ML. And now it's time for a presentation.
Thank you, Olga, for this nice introduction, and hello, everybody. So I just hope everybody sees my presentation. Yeah, it sounds fine. So the presentation today is about AI in production with TensorFlow, TensorFlow extended and Kubeflow pipelines. And in order to illustrate this topic and demonstrate the different components of our production ML pipeline, I will be using a use case that we have been developing at Renault Digital, which is called AI-empowered car diagnostic, or simply Diag AI. So let's start by presenting this project, Diag AI. So Diagnostic AI, or Diag AI, what is Diag AI and why are we developing this product, this AI-empowered or data-driven car diagnostic? So in plain terms, what would or should our machine learning model do? So the objective of Jag AI is to help dealers and the workshops find the root cause when they have a defective car. And why are we doing this? So in today's automobiles, the number of control units, the high tech features, the functionalities used in today's automobiles have increased tremendously. And with such rise in structure complexity and product variety, it becomes difficult for traditional diagnosis techniques to meet the requirements of fault detection and root cause analysis. So the objective is to drive the system to take faster and smarter diagnostic decisions that may help the company reduce warranty costs. In order to build our ML model, we use and merge several databases to create our ML datasets, let's say. So from the warranty database, we collect the replaced parts and operations carried out on the vehicles and the workshops. We also collect the automotive symptoms that promoted our customers to bring their vehicles to the workshops. And from the diagnostic database, we collect the onboard diagnostic data, which allow the repairer normally or the dealer to access the status of the various vehicle subsystems, such as the error codes and the other various sensor values. Just to explain, error codes, or usually we refer to them as DTCs, diagnostic trouble codes, correspond to faults detected in the vehicle since the last workshop visit. So an error code is mainly triggered and stored in the car if a particular sensor measures an abnormal value or an out of threshold value, let's call it. And then finally, we use other database to collect different metadata on vehicles, such as the car model, the engine type, the gearbox type, etc., and the mileage, for example, of the car. So what about the machine learning project lifecycle? So the Jag AI ML lifecycle is very similar to any typical ML process. The ML lifecycle can be summarized with the following diagram. In the first phase, before we get elbow deep in our data, it's important to set ourselves up for success. So therefore, alongside the business experts, we need to define our problem and the business model and the business needs. We need to answer some of the basic questions that allow us to take training and serving decisions regarding the decision of the model and the production pipeline. So for example, some of the questions that we need to be asking ourselves are, what is our evaluation metric? What are the success and failure criteria? How can we define the model's KPI? How can we identify if the system has succeeded or the system has failed? What data sources are needed for such objective? Are they available during serving? What are the latency requirements, and so on? So this is for the first phase. In the second phase, we prototype the first basic machine learning model, or in other words, we perform an ML feasibility study. Therefore, we prove the ML business value using the metric defined in the first phase. So remember, the best practices for machine learning engineering, rule number 1 is keep the first model simple and get the infrastructure right. The first model provides the biggest boost to our product, so it doesn't need to be fancy. And finally, in the third phase, we move to production. This is the main topic of our presentation, so we will see this more in details in the upcoming slides. And then once our production pipeline is ready, we can easily now iterate new ideas much faster and more efficiently. So we don't have to prototype each time a new model. We can go directly from phrasing the new business needs based on the insights we gathered, and then productionalizing the model again. So just before talking about the production AI pipeline, let's just talk a little bit about the machine learning model. So in order to reach our objective, we have tested several algorithmic approaches, such as association rules, association learning rules, random forest, and neural networks. One important thing to mention is that apart from the performance measures, there are other important criteria that need to be considered. Scalability, for example, production system stability, explicability, training time, and inference latency are all other important factors to take in our decision criteria. Neural networks, as you all know, I guess, are the fundamental elements of deep learning. So neural networks are widely used today because they can produce very high performance. They can also perform end-to-end prediction for all of our parts. In this example, for example, here we are predicting parts. It can do the end-to-end prediction at the same time, saving a huge amount of training and inference time. So, and using TensorFlow to develop our neural network offers a variety of extended production-oriented tools aligned to work with, which will allow us to design our end-to-end pipeline. The ML surprise, let's call it. So maybe this is not a surprise for everybody, especially for those who have worked in ML production. But people expect that they will be working much more on optimizing ML algorithm, whereas in fact, implementing and training an ML model with predictive performance on an offline whole data set, giving the relevant training data is relatively easy, depending on the use case. However, the real challenge isn't building an ML model. The challenge is building an integrated ML system and to continuously operate it in production. Only a small fraction of a real-world ML system is composed of the ML code. The rest of the system is composed of configuration, automation, data collection, feature engineering, testing and debugging, resource management, model analysis, process and metadata management, serving infrastructure and monitoring, etc. So an ML system is actually very similar to a software system. So similar practices apply to help guarantee that we can reliably build and operate ML systems at scale. However, ML systems differ from other software systems in many different ways. Like in development, for example, ML is experimental in nature, where different features or algorithms are tried to find what works best for our problem. The challenge is tracking what worked and what didn't work, and maintaining reproducibility while maximizing code reusability. An ML system also differs in testing, deployment, and production. We'll see that in the next slide. So in any ML project, after you define the business use case and establish the success criteria, the process of delivering an ML model to production involves the following steps. So the first step is data collection. This could be external. Data can be collected and used in a variety of different ways and projects. Then we have 5 main components that we will be talking about later in details: data processing, data validation, model training, model analysis, and model serving. And at the end, we set up a monitoring dashboard in order to track the live performance of our model. And then at the higher level, we also have the pipeline storage. So this could be, for example, cloud storage, which hosts the artifacts produced throughout the execution of the machine learning pipeline. And it could include, for example, data anomalies that have been generated from data validation component, transformed data and artifacts, exported trained models, model evaluation metrics, and so on. So these data will be used in by the next component or some external tool, for example, from the pipeline storage. And then we have the pipeline orchestration. We'll see that later. And of course, the front end integrated to our deployed model via REST API call. Let's talk more about each component. Let's start, for example, with the model training and model serving. So for model training and serving, we opted for using TensorFlow estimators. So why TensorFlow? TensorFlow allows you to focus on optimizing your machine learning algorithm while giving less attention to the boilerplate code that repeats itself every time. So if you're building something fairly standard, TensorFlow has a set of pre-made estimators that you can try out. You can also design custom estimators and wrap your own model that you would like to build from layers using, for example, TensorFlow Layers API or TensorFlow Losses API, and so on. As data and training time grows, your needs will also increase. So checkpoints allow you to pause and resume training when needed. So you can continue on training if the preset number of epochs happen to have to be insufficient, for example. Your data no longer fits in memory, for example. So estimators are designed with the dataset API, and the dataset API can handle out-of-memory datasets. We can also use TF records format, which will present an efficient format that works well with TensorFlow. The dataset API also supports nice features such as shuffling, repeating, and batching. You cannot train a large network over a large period of time without seeing how it's doing. So estimators can surface your defined metrics during training that you can visualize in TensorBoard on both your training and validation sets. TensorBoard is a TensorFlow's visualization tool, if you don't know what that is. So TensorBoard provides the visualization and tooling needed for machine learning experimentation. Before the last part, so you distributed training. So you cannot train a large network. You cannot train a large network over a large period of time without seeing how it's doing. So estimators can surface your defined metrics during training that you can visualize on TensorBoard. Sorry. Models can train for ages. Model can train for ages, for hours, for days, for weeks. So optimizing a model that takes multiple weeks of training is not workable. You have to distribute it on a cluster to make it faster. So going from one machine to many might sound complicated, but with TensorFlow and with AI platform, we'll see that later. It can manage the cluster automatically, so you get distribution out of the box. And finally, serving. So you need serving input function if you want your model to be able to make predictions. So the serving input function specifies what the color of the predict method you will have to provide. So you are essentially telling the model what data it has to get from the user. There are many ways we can serve our model. We can use, for example, TensorFlow serving. We can use TensorFlow Lite, which allows us to do TensorFlow models on mobile, embedded, and IoT devices. Or we can use AI platform, as we will see that in the next slide. So what about infrastructure? We'll talk here about AI platform. So AI platform training provides the cluster configuration for running automatically distributed TensorFlow training. So we can use AI platform to run our TensorFlow or scikit-learn or XGBoost training applications in the cloud. AI platform training provides the dependencies required to train machine learning models using these hosted frameworks in its runtime versions. We can also monitor the jobs with the GCP console. GCP means Google Cloud Platform Console. And once you have submitted a job to execute on AI platforms, there's a variety of ways to check on it. The GCP Web Console has a great UI for monitoring your jobs. You can see exactly how they were invoked, check out their logs, and see how much CPU and memory they are consuming. And then once our training job completes, we'll have a TensorFlow model ready to serve for predictions. So AI platforms provide a great infrastructure for this. AI platform will build you a production-ready web application out of your trained model. So it can offer batch service for your less latency sensitive predictions and a scalable REST API for real-time predictions. So AI platform online prediction is a completely serverless system, so you don't have to worry about any resource allocations. It will just scale out for you. Also, an AI platform, a model is actually a group of versions that has a default version as well. So this extra layer of abstraction and grouping allows us to seamlessly migrate traffic from one TensorFlow model version to the next. And finally, you will want to wrap your model to make it ready for AI platforms, hyperparameter tuning. So AI platform provides a service called Hypertune, which is hyperparameter tuning as a service. It supports grid search, random search, and Bayesian hyperparameter optimization, if you've heard of that. So as you can see here, this is the YAML file we sent to our job, and these we can track the performance of each trial inside the Hypertune service. So for those of you who maybe are not familiar with AI platform, AI platform used to be called Cloud Machine Learning Engine, or CMLE. So if you know that name, it's an old name, and then they changed it to AI platform recently. Now let's talk about data pre-processing or data transform. So the first step is to extract the new data from its data sources. The data is split, transformed, and prepared for the ML tasks. The outputs of this step are data files to train and evaluate the model and other metadata to be used in later components. Here, TensorFlow Extended provides a library called TensorFlow Transform, which enables the pre-processing steps to be replicated when the trained model is used to make predictions, such as when serving the model with TensorFlow serving or AI platform. Let's move to data validation. So in this component, we focus on the problem of validating the input data fed to ML pipeline. The importance of this problem is hard to overstate, especially for production pipelines. Irrespective of the ML algorithms used, data errors can adversely affect the quality of the generated models. Therefore, it's imperative to catch data errors early. The importance of error-free data also applies to the task of model understanding, since any attempt to debug and understand the output of the model must be grounded on the assumption that the data is adequately clean. All these observations point to the fact that we need to elevate data to a first-class citizen in ML pipelines, on par with algorithms and infrastructure, of course. So we need to provide the corresponding tooling to continuously monitor and validate data throughout the various stages of the pipeline. Tensorflow data validation, or TFDV, is a library for exploring and validating machine learning data. It is designed to be highly scalable and to work well with TensorFlow and TensorFlow Extended. TensorFlow data validation can analyze training and serving data and includes computing descriptive statistics. It also includes inferring a schema, as you can see here, and detecting data anomalies. So in detecting data anomalies, it performs validity checks by comparing data statistics against a schema that codifies expectations of the user. And it detects data drift by looking at a series of data distributions. It also includes scalable calculation of summary statistics of training and test data with Dataflow. You can use that with Dataflow. And it has an integration with a nice viewer, as these are screenshots from the viewer, to view stats, statistics, schema, and anomalies as well. Data validation and production pipeline. So in the case of continuously arriving data, new data need to be validated against the expectations codified within the schema. So in a typical setup, the schema is maintained across time. So from day one, you generate statistics about your data, and then you infer a schema. And then these statistics are, and then in day two, in a typical setup, statistics are computed over new data, and those statistics are then used to validate those new data against the original schema. The data statistics are also compared to the precedent data statistics to detect any data drift. For example, a new domain has appeared in your data. You can see in this diagram that the schema is inferred initially as a convenience, but it can evolve over time if you would like. Let's move to the model analysis component. So the model analysis component performs deep analysis of the training results and helps you validate your exported models. And they ensure that they are good enough, let's say, to be pushed to the later component, to be pushed to production. This evaluation step helps guarantee that the model is promoted to serving only if it satisfies the quality criteria that you set up. So the criteria include improved performance compared to previous models and fair performance on various data subsets. So the output of this step is a set of performance metric and a decision on whether to promote or not the model to production. So here we also use TensorFlow model analysis, or TFMA, which is a library for evaluating TensorFlow models. It allows us to evaluate our models in a distributed manner using the same metrics that we have defined in our trainer. So these metrics can be computed over different slices or segments, for example, like countries. As you can see, you can calculate the evaluation metric for every country in your data set, for every engine type, let's say, for every symptom, for every error code, and then you can visualize these performances. We can also track model performance over time so that we can be aware and react to changes, as you can see here. Let's move to monitoring. So ML models can have reduced performance, not only due to suboptimal coding, but also due to constantly evolving data profiles. So in other words, models can decay in more ways than conventional software systems. So you need to consider this degradation. Therefore, you need to track summary statistics of your data and monitor the online performance of your model. In order to do one of the three things: to send notifications, to roll back when values deviate from your expectations, or to potentially invoke a new iteration in the ML process. So as you can see here in our model decay, we can see that all the versions of model start to degrade and the performance start to decrease. And monitoring lets us detect this performance degradation and model staleness, and it acts for us as a cue for a new experimentation iteration and for a new retraining of the model on new data. And let's now move to, let's say, job orchestration or pipeline orchestration. So the level of automation of these steps defines the maturity of the ML process, which reflects the velocity of training new models, giving new data or new implementations. So a manual process could be common in many businesses nowadays that are beginning to apply machine learning to their use cases. This is considered the basic level of maturity. It might be sufficient when models are rarely changed or trained, but in practice, models often break when they are deployed in the real world. The models fail to adapt to changes in the dynamics of the environment or changes in the data that describes the environment. So a manual process can also be dangerous. It creates a disconnection between the ML part and the operation part. So it separates data scientists who work or who create the model and engineers who serve the model as a prediction service. And this process can lead to what we know as training serving skew. So the goal is to perform continuous training or automating the ML pipeline. With a manual process, you usually deploy a trained model as a prediction service to production, but with pipeline automation or pipeline orchestration, we deploy a whole training pipeline, which automatically and recurrently runs to serve the trained model as a prediction service. So the following list highlights the characteristics of the pipeline automation. So why do we do a pipeline automation? With pipeline automation, we can do rapid experimentation. So the steps of the ML experiment are orchestrated. The transition between steps is automated, which leads to rapid iteration of experiments and better readiness to move the whole pipeline to production. This also offers a continuous training of the model in production. So the model is automatically trained in production using fresh data based on live pipeline triggers. It also offers an experimental operational symmetry. So the pipeline implementation that is used in the development or experiment environment is used in the production or pre-production environment as well, which is a key aspect of MLOps practice for unifying DevOps. And finally, we have a continuous delivery and deployments of models. So an ML pipeline in production continuously delivers prediction service to new models that are trained on new data. The model deployment step, which serves the trained and validated model as a prediction service for online predictions, is then now automated. For this reason, we need an orchestrator. We will see in the demo later how we are going to use the Kubeflow orchestrator. So we need this orchestrator in order to connect these different components in the system together. The orchestrator runs the pipeline in a sequence and then automatically moves from one step to another based on some defined conditions. So in order to build hybrid machine learning systems that work very well on premise and in the cloud, let's say, so you need to have composability, portability, and scalability. So composability means that you need to compose a bunch of microservices together. Portability is a pipeline that works everywhere. And what's good at composability, portability, and scalability and containers as Kubernetes. So Kubeflow, that's why the Kubeflow is our choice of orchestrating the machine learning pipeline. We'll see more about Kubeflow in the demo. Now let's move to the next slide. So once the model is validated by the analysis component, by the model analysis component, the model serving component deploys the model as a REST API, which can be called from anywhere, as we can see. And that's where integrated front end comes. So this API is consumed by this web application that we have developed for our users. The user can use this application to enter the vehicle identification number of the vehicle concerned in the workshop to check the historical diagnostic data and the prediction of our model. So here, for example, our model recommends the traction battery. So we also indicate our model's confidence for this recommendation in order to tell the users how much confident is our algorithm. So now we're going to show you a video that we have prepared directly on Kubeflow on the monitoring dashboard and the web application. I'll let Olga play the video for you.
Kubeflow Pipelines is a Kubeflow service that lets us compose, orchestrate, and automate ML systems where each component or step of the system can run on Kubeflow itself, Google Cloud, or other cloud platforms. The Kubeflow Pipelines platform has a user interface for managing and tracking experiments, jobs, and runs. Let's go to one of our experiments. An experiment here is a workspace where you can try different configurations of your pipelines. You can use experiments to organize your runs into logical groups. A run is a single execution of a pipeline. In this window, Kubeflow pipelines allow us to trace the performance of the different runs of the same version of the pipeline. This is not only useful for experimenting new ideas during development, but also for tracing the performance of successive executions in production. This is an example of a pipeline run. A pipeline is a description of a machine learning workflow, including all of the components in the workflow and how the components relate to each other in the form of a graph. A pipeline configuration includes a definition of input parameters, which are required to run the pipeline, and the inputs and outputs of each component. Let's explore the data validation component. For the data validation, we mainly use Tensorflow Data Validation, or TFDV, which is a library for exploring and validating machine learning data. It is designed to be highly scalable and to work well with TensorFlow and TensorFlow Extended. TFDV can analyze training and serving data and includes inferring a schema, computing descriptive statistics of our data, and detecting data anomalies. Mainly two types of anomalies, which are it performs validity checks by comparing data statistics against a schema that codifies expectations of the user, and it detects data drift by looking at a series of data distributions. We can view these statistics and these anomalies in Kubeflow Pipelines UI in the artifacts, as we have seen. For example, we can compare the statistics of part root labels entity over here, which is the variable that captures the parts or the incidents or the operations, as we might call them, during this execution and the previous execution, to see how the distribution of the data has changed. Here we can see that new parts have been introduced in this new execution. We can also track data anomalies. Here we can see that the variable dealer country label in our training set was introduced to a new domain, China, which was not present during the previous executions. Let's move to the model analysis component. The model analysis component evaluates the model and ensures it's good enough to be pushed to production. The component outputs an OK or KO flag to the inputs of the next component in order to let it know whether it should deploy or not the trained model. TensorFlow Model Analysis, or TFMA, is a library for evaluating TensorFlow models. It allows us to evaluate our models in a distributed manner using the same metrics defined in our trainer. These metrics can be computed over different slices or segments of our data and visualized, like engine type, like country, like symptoms, error codes, etc. For example, here we can visualize the entity dealer country label. Let's select our evaluation metric, and we can see the performance of our model on different entities like country France, country Italy, Germany, etc. We can also track model performance over time and compare the performance of the current model to previous executions. We can run a pipeline implementation as many times as we like. A recurring run is a repeatable run of a pipeline. Let's create a new run. The configuration for a recurring run includes a copy of a pipeline with all parameter values specified, as well as a run trigger. A run trigger is a flag that tells the system when to spawn a new run, which could be periodic, for example, every 2 months or every 45 days. This is our monitoring dashboard, which allows to track summary statistics of our previously deployed models and generate useful insights. Here we can see how our precedent models are decaying with time. We can also look at low granular level performance of our model. For example, we can check the model's precision on each part or each operation. Our model is deployed as a REST API on AI platform. This API is consumed by the front end. We can enter the vehicle diagnosis, the vehicle's VIN under diagnosis, for example, this VIN over here. These are the various error codes triggered in our vehicle. We can look for the prediction of our algorithm here. Our model predicts this part. We also give the user an idea about the precision of our model on this particular part.
Thank you, Maggie, for an awesome presentation and for sharing your experience with us, what you've done at Renault Digital. And we have also questions. So we have a question from Bruno Desnet. He is asking, what is the cost by hour of AI platform?
So can you hear me, Olga?
Yes.
I can speak. Okay. So that's a good question. Where I never memorize prices because it's not me who pays. It's it's my company. So I don't have the exact numbers. But it also depends on whether you there's pricing for using AI platform training, which is different from using AI platform prediction. Also in training, it depends on what type of machine do you use, how many RAMs, how many CPUs, what is your cluster? Do you use accelerators like GPUs or TPUs, and so on? So it depends on these different things. What I can say is that I can send you some links in the chat where they set up their pricing, where they explain in details their pricing. Depends on what machine are you going to use or how much time. I'll let you know.
Yeah, that would be awesome. Thank you.
Yeah, I'll send some links now.
And tell me when it will finish. We have another question.
Yeah, just 1 second. Okay, and that's the second link. Yeah, what's the next question, please?
So the next question is from Nicolas Couturier. Is TensorFlow X stable? Have you
is TFX stable?
Yes.
Well,
have you encountered any problem?
Okay, so TFX is a recent project which has been developed by TensorFlow. When we started working, it wasn't that stable because it was in the beta versions. So we have encountered many problems, like some stabilities. Sometimes you install TensorFlow extended and it automatically updates your TensorFlow version, for example. We have encountered some of the problems. I don't remember all of the bugs, but now they have released the version 0.20, 0.21, and 0.22, which really sound quite stable. So we have been I am using these new versions on a new use case, on a new project, and I haven't encountered any problem so far.
Thank you for answering. Also, we have another question from Alexander Boyko. Why did Renault Digital choose GCP over Amazon Web Services?
Well, that was a strategic question. I think they had some package that they have signed with Google, and along the package that they have signed is to use Google Cloud Platform as a data center. Actually, when I presented this pipeline, this is quite a hybrid pipeline. The objective is to make it portable so that it can work on your local machine if you want. If you have enough memory or enough CPU, you can make it work on any cloud, on GCP and AWS. I know that AWS offer very equivalent services, so I don't think GCP offers something that AWS doesn't offer, or vice versa. They are very equivalent. Maybe they change a little bit in some minor details, but not in major details. But so yes, the choice between AWS and GCP is not really that important. So you can choose whatever platform that you like. The important part is that you do something modular, composable, and portable, and so that it can work anywhere you like. Because today our company have decided to work on GCP. If tomorrow this contract between Google and Renault has been has been renounced for some reason, and we have moved to AWS, then our pipeline should be designed to work on AWS as well in the same manner.
Thank you, Maggie. Also, a small reminder that we will have a networking part after the questions part, so stay tuned. And another question from Solomon Fang. How many full-time developers, scientists were involved in this whole project?
Two data scientists in this whole project too, and we were actually doing the data science part, which we designed the machine learning model and the architecture, and the data engineering part, or let's call it the machine learning engineering part, where we have designed the pipeline. We have coded the different pipeline components, and we have used the Kubeflow orchestrator. So it was us who have done everything. And the main issue was that it's very difficult to find data engineers to know about machine learning production, to know about MLOps. So that's why we had to take this responsibility on our own.
Thank you, Maggie. And another question from Alexander Boyko. Is it possible to run A/B tests for different models?
Yes. So the A/B tests should I think they should come in the next phase, where we do a CI/CD automation. What I mean by CI/CD automation, because in this presentation we have talked about the pipeline automation or the continuous training automation, but there's a next level maturity which is called also the CI/CD automation, and in this part we try to automate the changes in code, so that every time a new model is proposed, for example, by the data scientist, like a new feature engineering technique or a new layer has been introduced to our neural network, it is expected that we code our new model, and then in the CI/CD automation part, we push our code, and then it automatically takes these changes into consideration. So in order to take these changes into considerations, we need to perform A/B testing. But to be honest, we have finished our pipeline automation so far, and now in the next step, we will move to the CI/CD automation, where we will be doing many tests and including A/B tests for our different models.
Thank you, Maggie. I don't see any other questions. I think that they're finished, but I see a lot of grateful messages on our chat.
Yeah, thank you.
People tell you thanks, merci, Maggie, for your presentation. So yeah, thank you very much, Maggie, for your awesome presentation. It was very informative that people are writing on the chat. And yeah, thank you very much. So don't forget, we will have now a networking part, and the link will be in the chat. So join if you want to have video networking with other data scientists and other people. We will tell you in this chat also, Evgeny will tell you some machine learning news. And yes, we have another question from Ankur Inham. What's the timeline to build such model from scratch to production?
Okay, so that's an interesting question, because I already mentioned that the production of a machine learning model is the thing that takes too much time, or is the thing that consumes the more time in developing our ML system, and not the ML code itself or the algorithm itself. Developing this production pipeline depends on the skills that you already have. So when we started working on this use case, we did not know a lot about production AI and production pipelines, orchestration, and so on. So it have took us a couple of months in order, let's say 6 months, in order to develop this whole pipeline. And then we started iterating from then in order to enhance and improve our machine learning algorithm. But now, for example, I started working on a new use case, and it's not taking me that much, because I'm pretty much using most of the code that I've used in the old pipeline. So it's going to take me maybe a month or two maximum in order to productionalize the whole system. But it all depends on the use case, on the model. Here we're using tabular models. If we are doing something fairly for NLP use cases or vision use cases, computer vision use cases, it might be different. So it all depends on the use case as well.
Thank you.
You're welcome.
I think that's all with the questions. So don't forget, we have now video networking, link in the chat, where also Evgeny will tell us some news from machine learning. And don't forget, exactly in 1 week, we will have a third meetup where we will talk about Kaggle competition and first place solution, and also 11th place solution. So stay tuned. Thank you very much for your awesome presentation, Maggie, again, and thank you.
Thank you all. Maybe I have one last thing to mention is that at Renault Digital we're preparing a little training about MLOps and production AI. How can we use TensorFlow in order to develop our model? How can we use TensorFlow transform, TensorFlow data validation, TensorFlow model analysis? And we'll try to share the code with you, and maybe try to we will let you know very soon about some information regarding this training. So if you might be interested, you can join the open source training, or let's call it the free training that we are going to provide.
Thank you, Maggie. I think we will put the link, if we will write the code and this training, we will put the link in the comments to this video.
I don't have a link right now, so
yeah,
we are
after that.
Yeah. Okay. After that, yeah, we can do that.
Day.
Okay. Okay.
And yeah, thank you very much. Also, I would like to thank Evgeny Bazarov and Anton Doroshka, their other organizers. They've made a lot and huge impact. This meetup happened. So thank you very much.
Thank you all for your time and efforts.
Bye.